Hello, and thank you for joining us. We appreciate you attending today's much-anticipated webinar, The Rare Earth Magnet Supply Chain, Current and Future Status, which is being brought to you by Bunting and Design World magazine. Just a few housekeeping details before we get started. Additional resources can be found in the resource box, and we do encourage you to tweet with us. Simply sign in through the Twitter box. Today's hashtag DWWebinar is automatically added to your tweets. If you have any questions on the ON24 system or need any help, please refer to the help widget, which is located on the bottom of your screen. Now, if you have questions for our speaker at any time, please type those into the Q&A box, and we'll have time for Q&A after the presentation is over, and I will be glad to ask our speaker your questions. If you're watching this on demand, you can still use all the features that I just went over. Lastly, there is a bio widget with the presenter information. My name is Paul Heaney, and I'm the Vice President, Editorial Director for Design World. A little background on me. I have a mechanical engineering degree from Georgia Tech, and I've been covering the engineering and manufacturing worlds for more than 25 years. I'm pleased to be your moderator here today. Dr. John Ormerod has a PhD in metallurgy from the University of Manchester. He has more than 40 years of research, product development, and manufacturing expertise in the areas of permanent magnets and magnetic materials. John has published and presented numerous papers in the field of magnetic materials. He spent time in Europe working for Philips, and in the USA working for SPS Technologies / Arnold Engineering in their magnetic materials businesses. John has provided expert testimony on issues of invalidity during the recent rare earth magnet ITC investigation, and is currently a technical consultant evaluating prior art for the Rare Earth Permanent Magnet Industry Alliance. In 2015, John founded JOC LLC, a consultancy specializing in the magnetic and metals-related industries. He serves on the advisory board of Bunting and is Senior Technology Advisor to Bunting-DuBois. And now I will turn the floor over to our speaker, John. John, please take it away.
Good afternoon, everyone, and thank you, Paul, for that introduction. So as you just heard, my name is John Ormerod, and today I'm representing Bunting-DuBois as their Senior Technical Advisor. So the subject of this webinar talk this afternoon is the rare earth magnet supply chain. And I want to try and cover what's going on today, but also look, what the future looks like over this next decade or so. So what I hope to do in the next 45 minutes is, first of all, introduce you to the rare earths, the rare earth elements, explain their importance in permanent magnets, and then dive into the supply chain issues and finish up by offering, hopefully, some solutions to these current and future supply chain challenges. Now, in my view, permanent magnets are often overlooked, but they play a critically important role in both our technological and everyday lives. As most of you know, magnets are normally built into devices and therefore hidden from view and basically forgotten. But, as Intel so cleverly reminded us a few years ago with their Intel Inside campaign, magnets like chips and integrated circuits are also essential components that enable a wide range of key technologies from transportation to communication to medical science. And I would argue that magnets are equally as essential as chips and integrated circuits. So I always attempt to start one of these presentations with what I think is an interesting quote. And here's, let me do this. Here's today's. The nation that controls magnetism controls the universe. Now, some of you who've heard me speak before will have seen this quote, but I really like it. It's attributed to this gentleman, Dick Tracy, or more accurately, the cartoon strip created by Chester Gould, the author. Now, the first known reference I can find to this quote was in a comic strip appearing in the early 1960s. What's interesting, though, is that's way before rare earth magnets were a commercial product, and certainly before the Chinese dominance of the rare earth supply chain and the magnet industry. So, given the geopolitical situation we find ourselves in today, it's a quote that is obviously very relevant, and since it's almost 60 years old, it's even prophetic. So here are the subjects I'm going to attempt to cover in today's talk. First, I just want to do a quick introduction to Bunting, and particularly Bunting-DuBois, and I'll go over my background a little bit. Then I want to talk about the rare earth elements in, what are they, delve into those a little bit. Next, spend some time on the markets and key application areas for rare earth materials, and dig into the supply chain issues. Move on and describe the types of processing routes for the major rare earth magnet types. And then finally, talk about the actions and strategies being pursued to alleviate both the current and future supply constraints. Quick introduction to yours truly, although Paul did a pretty good job of this. Doctorate in metallurgy from Manchester way back in '78. I worked for Philips in '79 through '90, helped to develop and commercialize a range of rare earth magnets. Then I moved to the US in '90 and joined Arnold Magnetic Technologies, responsible for the magnetic materials development and GM for permanent magnets. Then in 2002, I moved and started and ran an automotive component manufacturing business in Wisconsin. I have spent a lot of time providing expert testimony on the key neodymium-ion boron attaching metal patents. Advisory board member for Bunting, technology advisor for Bunting-DuBois, CMI, and NP Materials. And then in 2015, I founded my technology consulting business. I want to talk about a little bit more detail about Bunting-DuBois, what they are, what they do. Now, you can get much more detailed information by going to the webshot site at this address shown on this slide. They're part of the Bunting Magnetic groups of companies. As far as I'm aware, they're the only North American manufacturer of compression bonded neodymium-ion boron magnets and injection molded ferrite neodymium-ion boron hybrid magnets. In addition, they supply the full range of engineered magnets and magnetic assemblies. They're located in DuBois, Pennsylvania, a couple of hours northeast of Pittsburgh. And then their primary applications for their products are brushless DC motors and sensors that serve the automotive, medical, defense, and industrial markets. In terms of services, they can provide pre-production magnetic design up to and including 3D magnetic modeling. They've got a state-of-the-art manufacturing capability, which does include in-house coating and a complete magnetic testing capability. They're one of the companies that are investing in R&D for the next generation of magnetic materials. For example, they've developed a high resonance compression bonded magnet, and they're working with Oak Ridge National Laboratories on 3D printed magnets. A family-owned business that have been in business now for over 60 years. ITAR DFARS registered, ISO 9000 certified quality system. And finally, they do have a really strong international supply chain, and so can supply the complete range of permanent magnet materials and assemblies. So let's talk about the rare earths and try and explain what they are. Now, the rare earths and particularly the Chinese domination of the supply chain have, it seems to me, recently become big news. So we have U.S. news here, mining the path to rare earth supply chains. Wall Street Journal, U.S. plans to spend big on critical minerals. Economist, in search of Greenland's rare earths. CNBC, the new U.S. plan to rival China and end cornering of market in rare earth metals. And then this final one is actually an interesting article that appeared in Physics Today earlier this year. U.S. government acts to reduce dependence on China for rare earth magnets. Now, these are obviously just a few examples of the articles that have come out in the last few months. But when you boil them down, they all have the same basic storyline, that rare earths are essential to our everyday life and also a lot of Department of Defense platforms. And oh, by the way, we're dependent on China. So let me dig into what the rare earth elements are in a bit more detail. The top left is showing the periodic table, and marked in blue are the rare earth elements. Now, the rare earth elements are one of a set of 17 elements in the table, specifically the 15 lanthanides, as well as scandium and yttrium. Now, scandium and yttrium are considered rare earth elements because they tend to occur in the same mineral deposits as the lanthanides, and they do have very similar chemical properties, but actually they have different electronic and magnetic properties. Now, despite their name, the rare earth elements are not particularly rare. So if you look at this USGS chart, the relative abundance of the elements in the Earth's crust, which I'm showing in the upper right here, you can see that actually most rare earth elements on average are about as abundant as tin. Now, their name comes from the term of being inert, like the rare gases, which, of course, itself is a misnomer, since, as we know, the rare earth elements are actually incredibly reactive. What happened was the early chemists mistakenly identified the stable rare earth compounds as the elements. Unfortunately, well, I'm not sure it's unfortunate, but the name rare has stuck. Now, in terms of mining and production, as we can see in this lower left chart, China still dominates the mining of rare earth elements. However, its dominance is weakening, and I'm going to discuss that in more detail later in this talk. And then finally, on this chart on the lower right, the U.S. Department of Energy a few years ago carried out a review of materials that are at risk of supply disruptions that are important to several clean energy technologies, things like wind turbines, electric vehicles, photovoltaic thin films, fluorescent lighting, and so on. And what you can see is that several elements key to rare earth permanent magnets are highlighted in the critical risk category. So we have neodymium, dysprosium, terbium, all in this category. And actually today I would also include praseodymium in this high risk area. This slide shows the relative abundance of the rare earth elements that are important to permanent magnet. And it also shows how we tend to divide the rare earth elements into two groups, the light rare earth elements and the heavy rare earths, which are based on their chemical similarities. So what you can see from this graph, or this chart, I should say, the heavy rare earths are much less abundant, typically than most of the light rare earths. And the other thing to note is cerium is by far the most abundant rare earth element. So I want to move on now and start discussing some of these issues surrounding the rare earth magnet supply chain and their markets. So, as you can see from the pie chart on the left here, as we just said, China does still dominate the mining of rare earth elements, but it actually only represents about 60% of the global mining of these materials. However, the key point to state is that China still dominates all the value-added downstream processing of these materials, including separation, reduction to metal, and magnet manufacturing. And I'm going to show that in a little bit more detail in a moment. Now, in the center here, I have a table that shows the major applications of rare earth elements. And the rare earth elements I've highlighted that are important for permanent magnets. So we got neodymium, praseodymium, samarium, terbium, and dysprosium. Now, on a value basis, the most important application for the rare earth elements is by far permanent magnets. The issue is really supply and demand for the individual rare earths, because, of course, nature did not match up the balance of the elements in the mineral deposits with the market demand. So as I just previously mentioned, some of these major minerals contain around 50% cerium, whereas the demand for that element today is probably less than 10%. And the figure on the right shows the quantities of rare earth elements that are used in some of these modern Department of Defense weapon systems. And as you can see from the mounts there, they use a lot of rare earths. Now, I've got to say, these are not only for magnets. There's a lot of other applications in radar systems and so on where the rare earths are used. But of course, it's not probably a great strategy to be dependent on China for these weapon system materials. So the Department of Defense is actually incentivizing the development of an integrated supply chain back in the USA. Now, having said that, I should note that as of today, in the US, there is zero commercial production of sintered neodymium iron boron magnets. But I also should mention that there is one company out there, Urban Mining Company, that has announced and is expected to be in production of sintered neodymium iron borons here in the US by the end of the year. There are three major, in my opinion, rare earth minerals: bastnäsite, monazite, which are both primarily light rare earth element minerals, and then the so-called ionic clays, or ionic absorption clays, that are the sources of the heavy rare earth elements. Now, the major sources of these materials outside of China are bastnäsite concentrate from the USA, ion absorption clays from Myanmar, and then monazite from Australia, Africa, Southeast Asia, and then I would include maybe Russia and India in that list. When you boil it down, though, today there are two major rare earth mines operating outside of China, and that's the Mountain Weld mine in Australia, which is owned and operated by Lynas Corporation, and then the Mountain Pass mine here in the United States in California, owned and operated by MP Materials. Now, these two operations together account for at least 30% of the global mine production of rare earths. So here is my attempt at simplifying the rare earth magnet supply chain way down to its basics. So what this slide is showing are the major steps in the from the rare earth element mine to the rare earth magnet supply chain. Now, the first step is, of course, mining the rare earth mineral from the ground, and that's what we've been talking about in the last few slides. Next, that material is further processed and concentrated, and then we follow up by separating the individual elements or mixture of elements. Now, because the rare earth elements are chemically very similar, conventional processing tends to be ineffective, and what's used is solvent extraction or some variant of that process. Now, in order to achieve a sufficiently high yield and purity of the individual rare earth element, we find that we have to use many, many solvent extraction cells, and these are all operate in series. So once we've got the separated rare earth compound, we then move on to reduction to metal, and finally magnet production. Now, what I'm trying to show in this bottom half of this chart is what I think is China's geographical dominance of each of these steps in the supply chain. And of course, these are my estimates. In my opinion, the Chinese chokehold in the supply chain is at two of these process steps. The first one is separation, and then the second one is alloy and magnet making. Now, I've heard some comments from experts in this industry that claim the magnet making process is relatively trivial. So all I can assume is that these comments are from individuals who've never had the opportunity to set up or operate a rare earth magnet plant, because trust me, it's far from trivial. So putting this slide together, I became concerned that my blue boxes made it look way too simple. So what I'm trying to show here is that each of these blue boxes hides some incredibly complex multi-step processes. And unfortunately, today, I just don't have time to go into the details of each of these processes, but I just want to make sure that everybody, I don't leave the wrong impression, because, again, there's some incredibly complex and demanding processes that, again, are far from trivial. So finally, in this section, I just want to do a quick reminder about what can happen to the prices of rare earth elements. And here I'm going back to 2011, 2012, when China and Japan got into some sort of territorial dispute in the South China Sea, and China announced they were going to restrict the export of rare earth materials. Now, the result was that rare earth prices increased dramatically, and for those of who were there, it felt like it was overnight. Now, for example, dysprosium prices increased almost 300 times and just became prohibitively expensive. And this actually led to a lot of extensive research efforts to reduce the dysprosium content in the higher temperature, higher coercivity grades. And I'll discuss that in a little bit more detail in a couple of slides. But the other thing to note is, after a few months, prices dropped, almost as rapidly as they increased, albeit they leveled out at a slightly higher level than before the price spike. So I want to move on now and say a few words about how we actually make rare earth magnets. So I'm going to start with the powder metallurgical approach, which is the most common method of manufacturing fully dense neodymium iron boron magnets. So here's I'm showing here an outline that's typical for that production process. Today, strip casting is the preferred method of alloy production. During strip casting, the molten alloy is cooled and solidified at around 10,000 degrees per second. This rapid cooling is found to develop the optimum microstructure and phase distribution for the starting alloy. The next step is coarse crushing of the strip cast alloy, which uses a hydrogen crepitation process, followed by jet milling to a narrow particle size distribution centered around 5 microns, and this produces a powder consisting of single crystal particles. That powder is then pressed under a magnetic aligning field, followed by sintering to full density, and then heat treatment to develop the final magnetic properties. Those fully dense parts are then machined to meet dimensional requirements, and then coated for corrosion protection, and then finally magnetized, and either at the magnet fabrication location or at the customer's location in the application. Now, there is a second processing method that was developed by General Motors, who later formed the Magnequench division. So Magnequench pioneered the use of melt spinning to produce an isotropic neodymium iron boron powder, which is used primarily in bonded magnet production, either compression bonding or injection molding. I mean, the principle of melt spinning consists of melting the alloy under vacuum or inert gas, and then that melt under inert gas pressure is sprayed onto a rotating water-cooled copper wheel or disc. In this case, cooling rates are actually in excess of 1,000,000 degrees a second, and it produces an alloy that is basically either amorphous glass-like or has a very, very fine-grained nanocrystalline structure. And again, these powders are isotropic, but they found a use in bonded magnet applications. So I'm going to move on now and look at some of the forecast supply demand issues we're finding with the rare earth elements. First of all, I'm going to talk about the light rare earths, and in particular neodymium and praseodymium. Now, let me say at this point, I mean, there's a wide range of experts talking about what the demand forecasts are going to be for these, for the magnets and these materials. And I could build almost any supply-demand picture you want to see. However, when you boil it down, in all cases, the demand picture is dominated primarily by the forecast growth of two things: electric vehicles and wind generators or wind turbines. So here I'm actually using a publicly available forecast from Arufura Resources, who are a company developing a neodymium praseodymium operation in Australia. So what you can see is they're forecasting that by 2030, 40% of the neodymium praseodymium will be for electric vehicles of some type, and another 11% will be for wind turbines. So in other words, over 50% of the neodymium praseodymium demand, and therefore the rare earth magnet demand, is going to be for those two clean energy applications in 2030. Now, what's more problematic is that they're showing there'll be a shortfall of neodymium praseodymium that's going to grow to 47,000 tons by 2030. And that's even with the known new projects and expansion projects. So that's the light rare earths. I'm now going to move on and talk about the importance of the heavy rare earths and explain, first of all, I'm going to try and explain their role in rare earth magnets. So one of the major disadvantages of neodymium iron boron magnets is the performance at elevated temperatures. So here's an example of the demagnetization behavior of a sintered neodymium iron boron grade N55M at different temperatures. So what you see is the effect of increasing temperature on both BR remnants and coercivity. Both those parameters decrease with increasing temperature, but in particular, this grade loses about 50% of its room temperature coercivity at 100 degrees C. Now, this is a major issue in an application that's operating at elevated temperatures, particularly when the magnets are going to be subject to significant demagnetizing field. So, you can think of an electric vehicle traction drivetrain motor, which typically works significantly above room temperature. So under high torque operating conditions, this could lead to demagnetization of the magnets and loss of motor performance or even total motor failure. So it's been known from the early days of neodymium iron boron development that the substitution of certain heavy rare earths dramatically improved coercivity. I mean, this chart is from actually a 1984 publication that shows the substantial improvement in coercivity by substituting dysprosium into the ternary system. So what's happened in the industry, it's become a common practice to add dysprosium or terbium to improve coercivity and therefore thermal performance and a maximum application temperature for these magnet materials. And here I'm just showing you the range of grade designations that are available today based on the dysprosium content and the maximum application temperature. So as you can see, by increasing the dysprosium content, we're increasing the maximum operating temperature of these magnets from actually around 80 degrees C up to 220. The issue is, though, to get performance at 200 or above, we're having to add about 10 weight % dysprosium. Now, here's the issue. The common minerals I've talked about of bastnasite and monazite contain very, very little heavy rare earths. They're primarily light rare earth minerals. And today, the major sources of dysprosium are these so-called lateritic ionic clays that are really only found in two places today. One is southern China, and the other is Myanmar. So that does cause us some indigestion, to say the least. Now, some of these forecasts, again, are actually painting a rather bleak picture of the future supply of dysprosium. Once more, I'm using a publicly available forecast. This time it's from Adam Mass Intelligence. But as you can see, I mean, they're showing a dysprosium supply deficiency even today. And that gap is growing through the decade as the demand for EVs and wind turbines accelerates. So the question is, what are we going to do to mitigate these supply issues, given some of these very, very robust demand forecasts? So in my view, there's several strategic initiatives that are already underway. I mean, the first one is government intervention. The second is reduction of rare earth consumption. And then we have new expanding rare earth sources and supply chains. And finally, we have new lower rare earth or non-rare earth magnet materials. So let's talk about each of those in a little more detail. There are several federal initiatives already underway, primarily through the Department of Defense or the Department of Energy. That we do have the executive orders on supply chains that are actually coming from both the previous and the current administration. We have Department of Defense funding for Linus's planned separation plant in Texas, similar funding for MP materials, and then Department of Defense funding for Urban Mining Company. And then interestingly, just last month, a bill was introduced in the House designed to provide tax incentives for the U.S. production of rare earth magnets. And essentially, there'd be, for magnets produced here, there would be so many dollars per pound or kilogram tax credit. And then it would be a higher number if those magnets were produced with U.S. sourced raw materials, rare earth raw materials. How far this will go, who knows? But it's kind of an interesting concept. Okay, let's talk about the reduction of rare earth consumption. So I talked earlier about the need for heavy rare earth elements in these higher temperature grades. And actually, over the last 5-7 years, a technology has been developed that is known as grain boundary diffusion. And essentially what's happening here, without getting into all the details, is that the heavy rare earth elements are placed at the grain boundaries of these materials, of these magnet materials. And that's important because that's where the coercivity is determined and not throughout the bulk of the material. And essentially, you can reduce the dysprosium requirement for a particular thermal grade by about 50%. And then we've got the ongoing modification of applications, the redesign of applications to reduce the requirement for super high intrinsic coercivity, thus reducing the need for heavy rare earths. And at the same time, what I'm seeing, particularly with some of the electric vehicle traction drive motor designs, they're also reducing the actual volume of magnet material that are required in those motors for the same performance characteristics, and therefore the amount of even light rare earths is being reduced. Then we have the expansion of cerium and in some cases lanthanum grades for use in less demanding room temperature applications, and then finally recycling. Now, some amount of recycling has been part of the manufacturing process since commercialization of these magnets in the mid-80s. In my view, the key is to be able to economically viably recover and recycle end-of-life magnets, which today is and when I say end-of-life magnets, I mean from hard disk drives, motors, other devices. Today, that's a relatively minor contribution, but it's going to grow rapidly in the next decade, and I believe become a very important source of these of rare earth elements. Let's talk about new and expanding non-Chinese rare earth projects. MP Materials is already producing significant quantities of rare earth element concentrate and are expecting to have separation capabilities online in the next 12 to 18 months. Now, in addition, they've also announced plans for downstream value-added steps of metal making, alloy production, and magnet manufacturing, but these are, of course, longer term plans. USA Rare Earth have announced a mine-to-magnet plan based on their Round Top source in Texas, and they did acquire the ex-Hitachi Metals Limited equipment from their facility in North Carolina. Neo-performance materials and energy fuels is another potential U.S. non-Chinese solution. So we have monazite sands that are mined in Georgia. They're shipped to the Energy Fuels Utah facility to remove the radioactive elements, and then that mixed rare earth carbonates are shipped to Neo-Performance Materials facility in Estonia for separation. Now, admittedly, this is the moment is a very small-scale operation, but it's certainly a move in the right direction. Now, in addition, there's dozens and dozens of junior miners with projects at various stages on every continent around the world, and here I'm just listing a sample of those. And at the bottom, there are also a group of companies who are involved in novel separation and recycling efforts. So, what about a new rare earth-free magnet material? So what I'm going to try and show you here is where we came from and where we are today. So here's a chart that shows the historical development of permanent magnets based on their maximum energy product. And what you can see in this chart is the dramatic improvement in performance, beginning with the magnet steels back in the early 1900s, to the alnicos in the 30s, 40s, and 50s, and finally hard ferrites and rare earth magnets exhibiting very high coercivities starting in the 60s through today. So, but what's interesting to note is that there's really been no major new material introduced since neodymium ion boron in the early 80s. So it's now over 35 years since the announcement of those magnets. And as I said on this slide, it does pose the question that after all this time, is it time for a new magnetic material breakthrough? So, why is it we're still waiting for the next big thing to replace neodymium ion boron magnets? So, believe me, it's not for the sake of trying, but discovering new materials and compounds for permanent magnets is actually a really, really difficult task. First of all, you've got to find a composition or a phase with a uniaxial crystal structure that demonstrates the intrinsic properties of magnetization, anisotropy field, and Curie temperature. Then, if you've discovered that, you've then got to be able to create a microstructure with that material that impedes reverse domain nucleation and growth. Plus, for an anisotropic magnet, you've got to develop a microscopic texture. And finally, even if you've got those two difficult challenges solved, you've then got to be able to fabricate useful bulk shapes in mass production volumes. And the reason I say that is because I've seen some interesting properties in some systems that have, been developed through sputtering or ion implantation techniques, which is fine if you need a few grams of a very thin foil. But in my view, it's not practical for producing thousands of tons of bulk product. So, we need a manufacturing process that can be readily and economically scaled up. Now, all those problems are going to be solved within a very small overlapping window to be able to commercialize a new magnet with the necessary extrinsic properties of remnants, energy product, coercivity, the thermal, chemical, and mechanical properties. And of course, the economics of the raw materials and processing have to be commercially viable. So, perhaps it's not surprising we're still waiting, despite the enormous amount of R&D effort that has been put into this goal around the world. Now, it's almost impossible to show you all the developments that are going on. So here's just a snapshot of some of the new magnet material developments. The concept of exchange spring or nanocomposites has been known since the 80s. Now, simply, they're a combination of a hard and soft magnetic phase that interact and combine the high magnetization of the soft phase with the high coercivity of the hard phase. However, in order to develop the required exchange mechanism, a very precise phase size, morphology, distribution, interface separation is necessary. And this is just proven to be so far a significant challenge to reproduce in bulk materials. Fe16N2, or iron nitride, is somewhat the holy grail of permanent magnet materials. It's got high magnetization, there's no rare earths, and essentially it's iron. But synthesizing the compound and developing significant coercivity has proven elusive to date. Cobalt nanowires have been developed with energy products of 44 megagauss Oersteds, which is very impressive. However, cobalt is not the ideal raw material for permanent magnets. And then there's numerous other compositions I'm showing in this yellow box here that have been discovered: manganese aluminum, manganese bismuth, zirconium cobalt, hafnium cobalt, and so on. But none of them have the raw material benefits or properties or economics that can rival the compound Nd2Fe14b. So I just got to acknowledge that neodymium-ion boron is an incredible product and really excellent in terms of a mass market magnet material. So let me just summarize what I've been trying to say here. First of all, I talked about government intervention, and it's essential, and some of it's happening. But I do have a concern that it seems to be focused on certain portions of the supply chain, because for it to be effective, it needs to address the total supply chain. And by total supply chain, I mean through to the people, the companies that are building devices that are using magnets, and to the OEMs. They need to be part of this solution. Reduction of rare earth consumption. I hope I've shown that there's a lot of activities in that area, and it is happening. New expanding rare earth sources, supply chains, it's happening. Now, new lower rare earth, non-rare earth magnet materials. In my opinion, it's going to be very difficult to directly replace neodymium-ion boron. But I do expect materials that have niche properties, niche applications are going to be introduced. But I do have to make this final point here, because, we can't get away from it. China does have one very important lever today, and that is basically they can control the prices at each step of the supply chain. And I just want to say that because this is the reality today. So we're almost at the end of this talk. But having put this talk together and going through it, I felt it sounded a little on the pessimistic side, which certainly wasn't my intent. But I don't know how the audience felt, but that's how it came across to me. So I do want to finish on a high note, and I want to show one last slide that's showing it's possible to have a non-Chinese rare earth magnet supply chain. So here it is for bonded magnets from Bunting-DuBois. So the raw material or the mineral is mined at in Australia at the Lynas mine from their the Mount Weld operation. That concentrate is then shipped to Malaysia to the Lynas's separation facility. The neodymium praseodymium separated compound is then shipped to Thailand, where it's reduced to metal and then magnequench melt spins or jet casts the alloy to powder. That powder is then shipped to Bunting-DuBois in Pennsylvania, where they make compression bonded or injection molded magnets, neodymium-ion boron magnets. And the picture here is just showing a couple of injection molded magnets that look like they're on over-molded onto a shaft. But the point is, this is a totally this never touches China, and it's a rare earth magnet supply chain. So with that, I'm going to thank everybody for being here today. I really appreciate your attention, and I will attempt to answer any questions you have. But if you want to contact me, any of these email addresses work, or you can call me anytime, and I'm happy to chat. And thank you again for your attention, and I'll attempt to answer any questions.
Thank you so much, John. All right, we will now use the remaining time for questions. We do have several that have been coming in, but remember, it is not too late to send in your question. Simply use that dialog box on your screen to type it in. All right, John, you ready?
I think so. Yeah.
Right.
Are you going to go ahead and ask?
Yeah, I'll read the questions aloud to you.
Okay.
So the first one, and I think you kind of answered this a little bit toward the end. What are the major sources of non-Chinese rare earth elements today?
Yeah, I think I covered that, but it's obviously Mountain Pass, Linus, are the two, are the two major sources. I mean, there's other sources in Southeast Asia, Russia, India, but 30% of the if China's 60%, those two operations are 30%, and the rest are 10%.
Okay. What is the most critical step or process in the rare earth magnet supply chain?
Oh, well, again, I attempted to cover that. I mean, this is my opinion. I think it's the separation step because it's an incredibly capitally intensive process. It's very difficult to operate economically. And then the second is, I think, is the actual magnet making, alloy making and magnet making. Are the two, I think, are the two critical steps in this supply chain.
Okay. All right, here's an in-depth one. You ready for this? Can you do a deep dive on Afura's 40 kiloton per year shortfall by 2030? Oxide, metal? Also, can you cite any definitive reference on the amount of NdPr oxide produced in 2020? I have found some significant differences in this number between varying consulting groups. Any thoughts there, or do you want to get back to them later on that one?
That sounds like Stephen McGuire. Is that who it is? I mean, that's just too. Can I respond to that when I've got a little bit more time?
We can take that one off.
It's a great question, but I need a little bit more time.
Very understandable. All right. With the current demand, what is the current lead times OEMs should consider, and how much longer looking forward?
Is that referring to magnets?
I believe so, yes.
Okay. I mean, I'm seeing lead times of recently of 3 months. How long is that going to take to get back to normal? I don't know. All I know is I've been looking at new cars, and the dealer tells me it's not going to get back to normal until the second half of next year. So if that's any indication, that's when I think things will get back to, where they were pre-COVID.
And I've even heard 2023 on the car.
Yeah, it's possible. Too. I mean, maybe that was wishful thinking on his part.
All right, next question. So the positive note you finished on is for bonded, but what about sintered, which are prominent in EVs?
I mean, today, I think the one operation that is going to look like the picture I showed for bonded is probably this urban mining company operation here in Texas, who are planning to use end-of-life magnets from, I think, primarily from disk drives, but I'm not 100% sure about that. That's the closest that I'm aware of.
Okay. Next up, is helium used in the production of rare earth magnets, and how secure is our supply of helium?
I don't think helium's used. It's just too expensive. Argon and to some extent nitrogen are used, but I don't think helium's used. I've never known it to be used in a regular production of these materials.
Okay. Was the Mountain Pass mine used to mine uranium? If so, what are the primary rare earths that are available from this mine?
I don't think it was used for uranium. I think it's primarily a bastnasite deposit, and it's primarily light rare earths. A lot of cerium, some neodymium, some praseodymium, and so on.
All right, here's something that occurred to me, and I'm glad someone else asked it. Are rare earth elements available on the moon or asteroids? Look a little down the line.
Wow. I don't know. I don't know. I mean, it's a good. I do not know.
All right. Any issue regarding uranium thorium during the separation of HMS?
HMS. I mean, as far as I'm aware, the radioactive issue is not so much with bastnasite. There may be some low levels. I think it's primarily in the monazite deposits where you get more thorium, uranium amounts. Because, for example, I know the monazite sands coming out of Georgia have to go to this Energy Fuels Utah facility where they separate out the radioactive components.
All right. Someone asked, how many of these separation/processing steps are non-U.S. due to health or environmental concerns, would you say?
Well, I don't know how to answer that really, but I mean, all I can say is I know that, NP Materials have publicly announced that they're going to be, they're building a separation facility at the Mountain Pass mine in California. And clearly, I'm guessing California is probably the most stringent in terms of environmental requirements. And, they're going ahead and doing that. And so that's the best way I can answer that question, I think.
All right. Will the new domestic sources generally be for military, or will it provide for consumer products as well?
Well, if we're talking about sintered, well, let me back up. I mean, the bonded magnet supply chain I showed for Bunting, that's for any market, any industries, for sure. The urban mine, and I don't know this for sure. This is pure speculation. I mean, all I can say about the urban mining sintered operation is the Department of Defense have put in, significant dollars. So, I guess, draw your, we got to draw our own conclusions from that. But I have no inside information other than what I see.
All right. Any thoughts on rare earth deposits in Mexico?
I'm not aware of any, but that's not to say there aren't. But I'm not aware of any active, mining exploration going on. But again, I mean, I should say I think I said it. There's dozens and dozens of these junior miners, and I can't keep track of them all. So there could be, but I'm not. Nothing springs to mind.
All right, John, we got time for one last question here. You mentioned that there are 2 mines outside of China that produce 30% of the world's magnets, if I understood correctly.
Okay.
By how much percentage could the rest of the world increase their production of rare earth elements?
Well, what I tried to say was there's 2 mines operating outside of China that produce 30% of the mined rare earth elements, and that's the Mount Weld mine in Australia, Linus's operation, and the Mountain Pass mine here in California, run by NP Materials. So that doesn't mean there's 30% of the neodymium iron boron magnets are produced outside of China. That's not the case, because I think China, I think I said in my slide, probably have 80 to 85% of the global production of neodymium iron boron magnets. So again, I don't know if that answered the question, but I can take a look at all these questions, and after this webinar finishes, and I will hopefully, I'm assuming I get email addresses, and I'll try and respond in more detail.
Perfect. All right, thank you, John. And a big thank you to everyone for attending this webinar from Design World and our sponsor, Bunting. This presentation will be emailed to everyone in the coming days, and it will also be available at designworldonline.com. Don't forget to include the hashtag DWWebinar if you discuss what you've learned here today on social media. Thanks once again to John for all of his insights. Have a great rest of your day, everyone. Goodbye.